Okay, you can begin now.
Okay. Hello. Thank you very much for having me back for a second lecture. Um, so let me share the notes. And well, last week, this is the second lecture, as you can see, on real representations of finite groups of Lie type. And last week was a bit of an introduction. What are the main questions? What are the main concepts? Some important examples, and then we finally looked at this one situation for GLN. And so today we'll go a little more in depth in terms of what's known, um, how things have been figured out, and some conjectures and some open problems. I'll list some. Of course, there'll be the big conjectures, but there will also be some open problems that are very, I think, doable and good problems that need to be answered. So instead of exercises, there will be some research problems listed. Okay, so just to remind you what we were talking about, Brouwer's 14th problem. So this is in a paper of Brouwer that was published in 1963 with a long list of questions from finite group character theory. And this was the 14th problem in this list. Describe the number of irreducible complex representations which are defined over the real numbers for a finite group G in terms of group theoretic data for G. So the motivation for this is that if you just look at the number of real valued characters, this is equal to the number of so-called real conjugacy classes of the group. That is the number of conjugacy classes such that G is conjugate to G inverse. And so this is asking for some kind of answer in the same flavor. So just in terms of group theoretic properties of G for the number of characters with Fabini shear indicator 1. So they have real valued character and they are afforded by a representation that can be defined over the real numbers. And a subproblem we talked a bit about last time, classify the finite groups so that all of the representations are orthogonal. So every single irreducible character has Fabini shear indicator 1. So, of course, the main topic is about groups of Lie type. And one of the things I was trying to get at last time was the geometry should tell us something good. And we went through examples of Weyl groups and all kinds of classes of Weyl groups there and normalizers of parabolic subgroups. But I wanted to give a few results, namely 2 results in the general direction. So this question, I mean, Gao was interested in this question when he was looking at the general linear group over a finite field, and we talked about some of his results last time. So here's a very nice result for a finite group in general. It's a partial answer to this. If your finite group has a Sylow T2 subgroup, which is abelian, then all of the real valued characters have indicator 1 if and only if all real classes are strongly real. So last time we talked about strongly real. These are real classes so that each element can be conjugated to its inverse by an element which squares to the identity. So we saw that these concepts line up for all of the finite Coxeter groups last time, normalizers of parabolic subgroups in finite Coxeter groups. And so here, what we're saying is of course, those Sylow 2 subgroups may be very non-abelian, but there's something about the geometry guiding things there. In this case, regardless of the finite group, if it's abelian, if its Sylow 2 subgroup is abelian, then somehow that is enough to give this correspondence between all real valued characters being orthogonal and all real conjugacy classes being strongly real. On the other hand, so the Sylow 2 subgroup being abelian is restrictive. There are lots of 2 groups, too many 2 groups. So Kostresta is here today, I saw. So this is a very nice construction. So this is kind of on the other hand, if we were to not restrict the CLF2 subgroup, the question becomes extremely difficult, it seems. So this is from a paper of Kaur and Kocheresta in 2015. If you look at special two groups, so you don't have to look that far. Special two groups, you can write down they're a very specific family of two groups. But for every m at least 5, there's a special two group of order 2 to the m, which is strongly real but not totally orthogonal. And vice versa, for every m at least 7, there's a special two group of order 2 to the m, which is totally orthogonal but not strongly real. So who knows how much more complicated things can get if you look at every finite two group. But it seems just from this construction that two groups present a problem for this to have a reasonable answer for finite groups in general. That seems like a very difficult problem. And so that brings us back to the geometry. Now maybe something more can be said for two groups, but I have a feeling if one looks at finite two groups and tries to get some kind of answer for this, then there's going to be some heavy cohomology and a deep understanding of constructing two groups that's needed, but that seems hard. Okay, so one way that group theorists try to get an answer to all finite groups is to look at what's going on with finite simple groups. So there's a classification of finite simple groups. And so one question that was addressed by Tiepp and Zaleski, this is in a paper from 2005, is, okay, which finite simple groups are real? That is, which ones have the property that, well, one, all classes are real, so every element is conjugate to its inverse, or equivalently, all of their characters are real valued. So Tiepp and Zaleski classified all such finite simple groups, and here's a list. And well, afterwards I realized, and I jokingly almost sent in a correction for the paper because they forgot to include Z mod 2Z, the two element group. Of course, this is a silly one, but it's there. So here are all the finite simple groups so that every single character is real valued. So first in the list, there's just two sporadic groups, these J1, J2 Yanko groups. I don't know much about them. I only know the list of sporadic groups. Only two alternating groups. Most alternating groups have elements that are not real, most of them. So just two of them are strongly real. And then here's an exceptional group, the Steinberg triality group. So you can twist Frobenius maps by various automorphisms of the group. D4 has an order 3 graph automorphism if you look at its Dinkin diagram. And so the Steinberg triality group is obtained by twisting Frobenius by this order 3 graph automorphism of D4. And so that one happens to be strongly real. Then we have a list of simple groups of Lie type. So we have first this list of just 4 groups, and then an infinite family of simple groups of Lie type. And not all simple groups of Lie type. You don't see any PSLs or PSUs here. So the simple symplectic group, so we have to mod out by the center. As long as Q is not 3 mod 4, those are strongly real. And then these are for simple orthogonal groups. Well, this is an index 2. Omega is an index 2 subgroup of the special orthogonal group in general. It's the derived subgroup of the orthogonal group. Sometimes it has a center, so sometimes you have to mod out by the center. But anyway, there's this list of simple orthogonal groups under certain conditions where things are strongly real. Sorry, where things are real. Things are real. So by Tiepp and Zaleski, these are exactly the finite simple groups which are real. And I said strongly real. That's a bit of a spoiler, but for the 5 to 6 years after this paper, there were a lot of authors who said, okay, which of these are strongly real? And it turns out all of these real simple groups are strongly real. So kind of a surprising result for finite simple groups is that every element is conjugate to its inverse if and only if every element is conjugate to its inverse by an element which squares to the identity. And there's so there's some other history to this. There is a problem listed in something called the Kurovka notebook, which was a Siberian mathematician. So there's a group of mathematicians at a Siberian mathematical institute who worked on this problem and got a lot of these things classified, and finally finished in 2011. I believe the last one that was covered was the case when Q is a power of 2, and we look at P omega. Well, there's no P, there's no center when Q is a power of 2. So omega plus or minus 4mq. So that was the last case proved by a Finnish mathematician. At any rate, every finite simple group is real if and only if it's strongly real. Kind of surprising. Okay, so that's done. That's classified. So now the question is, what about the characters? So all of these things have all real valued characters. Which of their characters have the property that they are also all orthogonal? Can be defined over the real numbers.
So
yes, go ahead. Yes.
So this alternating group 5 or 6 also real, right? Or
I'm sorry. One more time.
A5 and A6.
A5 and A6 are covered by. They are, so there's these small group isomorphisms, right?
Okay. So
So those are covered by, so for example, the symplectic group, we take n greater than or equal to 1, which includes PSL2 for various Qs. So you get those small alternating groups through these. Yeah. But you are right, and there are these small, so sometimes there's these statements I'll say later where I might say for all but finitely many, because these small group isomorphisms sometimes crop up. But you're absolutely right. There are 2 more alternating groups, A5 and A6, that happen to also be simple groups of Lie type for small group isomorphisms. Thank you. Okay, so what about their characters? Well, so the handful of non-simple groups of Lie type, you can look at their character tables in the atlas. This mammoth work of computing character tables, where these sporadic groups are covered, and all the indicators are listed of these groups. And you can see these groups are totally orthogonal. They're strongly real. They happen to be totally orthogonal as well. So the rest, after that, it's really a question about groups of Lie type. And what my main point that I'm going to get here is that I think when this question was asked, maybe we asked things about the simple groups. The answer that came out was, it's not really the simple groups we care about. It's these groups of Lie type that have nice properties. And right, which of course is the topic of the talk, so no surprise there. So what's going on with these groups? Well, we can just go down the list for a lot of them. So we've got this finite list. And then the Steinberg triality group, this was covered in a paper of Barry, who was actually, I believe, a student of Rodgau, and showed that this group, the Steinberg triality group, when Q is odd, that's totally orthogonal. And there's a generic character table for this group. And when Q is even, you can also get the information that it's totally orthogonal. So that group's totally orthogonal. Now, the rest of these groups all come from either an orthogonal group or a symplectic group. Well, these come from symplectic groups. The rest come from orthogonal groups. And when Q is odd, I mentioned last time that in the 1985 paper of Gao, he proved that special orthogonal groups with, when Q is odd, that's very important, with dimension either odd or dimension divisible by 4, these are all totally orthogonal. And these facts alone are enough to go down and conclude that all of these, when Q is odd, are totally orthogonal. Not when Q is even, we don't have that information, but when Q is odd, these follow from Gao. And Gao also showed in the same paper that when Q is odd and you take a symplectic group, then a character that is real valued is orthogonal if and only if the central character, that is the character on central elements of G, is trivial. So if this acts trivially on minus identity, then this is orthogonal. And if it doesn't act trivially, then this is symplectic. So this is enough when we mod out by the center, where the center is the thing guiding whether this thing is 1 or minus 1. If we mod that out, then we get that when Q is 1 mod 4, because 1 mod 4 is the case where Q is odd and this is totally orthogonal, one gets that this thing is totally orthogonal. Okay, so previous work, in other words, once this was all done, previous work all covers every group except for the symplectic group when Q is even and the simple orthogonal groups when Q is even. Okay, so one of the things that I'll do today is give an outline. The details are boring, but the outline I think is interesting, of the following result, which I managed to finish in 2020. Well, I didn't actually do the research in 2020, but that's when it was published. So if Q is a power of 2, then the groups, the symplectic group over the field of Q elements, the full orthogonal group over the field of Q elements, and the simple orthogonal group of dimension divisible by 4 over a field of Q elements, these are all totally orthogonal. And if you look at, so a little more information, if you look at dimension 4m plus 2, all of the real valued characters of this simple orthogonal group, all the real value characters are orthogonal in this group. It's not totally orthogonal, but we have no -1 indicators. Okay, so I'll give an outline of this proof a little later. But here's the main result we can get from this. So after all of this stuff, if you put it all together, what we get is a finite simple group is strongly real if and only if it is totally orthogonal. So that's a very nice statement for finite simple groups. However, what this is really saying is that for finite simple groups of Lie type, this is true. And there's these 4 other groups. So I view it more as a statement about these finite simple groups of Lie type. Okay, well, it'd be nice if we could look at other finite simple groups of Lie type and have some statement about those as well. So I want to look at, other finite simple groups, what's going on. So the only sporadic groups that showed up in this list that were strongly real were these 2 Yanko groups. If you look at sporadic groups that aren't real and you start looking at what are the indicators, what is the status of the reality of the classes, well, only one of the 26 sporadic groups has a symplectic character, and it's the McLaughlin group. It has 2 symplectic characters, and it happens to have 3 weakly real classes. So all of this can be done in GAP. These character tables are stored in GAP, so one can go through a computation and get this information. And then there's this list of several other sporadic groups that have 1 weakly real class but no symplectic characters. So these couple of Mathieu sporadic groups, the second Conway, the Harada-Norton group, the Thompson group, these each have 1 weakly real class but no symplectic characters at all. And then the monster group, of course, always the troublemaker. The monster group has 10 weakly real classes and no symplectic characters. So this is a little weird in that this is kind of weird behavior. I mean, one might hope that maybe you have strongly real classes if and only if there's an orthogonal. You have all strongly real classes if and only if there's some orthogonal character, but there's weird things happen. So this is things where there are no symplectic characters, but there are weakly real classes. Well, there's a weakly real class, and then the monster group, there's even 10 weakly real classes and no symplectic characters. So part of the point I'm making is that these finite simple groups are not well behaved. It's really the finite simple groups of Lie type. So I'm going to give some evidence for the following conjecture and give you some indication of what's left to do. So if we have a finite simple group of Lie type or an alternating group, then G has a symplectic character if and only if G has weakly real classes. So there's a whole bunch of cases that are covered for this, and I'll start to list some. But this is, I really believe that this question about the simple groups was maybe a misplaced question. Well, it's a good question, but you don't get a good answer for the simple groups that are not finite simple groups of Lie type. At least no obvious good answer because of this weird behavior. Okay, so I want to look at some exceptional groups because in that list of real simple groups of Lie type, they were all classical except for the Steinberg triality group. That was the one exceptional group, but there's some interesting behavior in the exceptional groups that provide some evidence for this conjecture. So I'd like to look at these exceptional groups for a little while, and I'm not an expert in exceptional groups, and that means that I'm going to list them all and explain kind of where they come from because it's something I don't know extremely well myself. So what is an exceptional group of Lie type? So first, you start with a simple algebraic group that's defined over a algebraic closure of a p-element field, and you take some Frobenius map or Steinberg map. So when I say Steinberg map, that means we can twist a standard Frobenius map by any number of automorphisms. And so these things are sometimes called Steinberg maps. They generalize Frobenius maps. So if G is a simple algebraic group that is of exceptional type, this just means it's not classical. This means G can be type G2, F4, E6, E7, or E8. And what are the finite groups that come out of this by choosing a Frobenius or twisted Frobenius map? Well, we get G2, F4 over Q. Then, well, so since I'm starting out with a simple algebraic group, you had this course on classification of, or I'm not sure how deep you went into the classification, but simple algebraic groups you can completely classify, and they, in terms of E6, they can come in type a type that is an adjoint group or one that is simply connected. And I'll talk about the difference here when you come down to the finite group part. You can twist E6 by a graph automorphism, so you have adjoint and simply connected. E7, well, you can have adjoint or simply connected. Then E8 is just E8, stands alone. There's only one simple algebraic group of type E8, and we get the finite simple group E8Q. Then there are these couple of funny groups. These are both called Re groups, REE, and these come from kind of a number theoretic twist on the standard Frobenius map, which one can get with certain number theoretic considerations. I mean, for G2, you can only twist by this if you're in characteristic 3. And in F4, you can only have this certain twist when Q squared is a power of 2. And there's something funny here. Q is no longer an integer. So you're still starting out over a field that is a algebraic closure of FP. But then what we're doing is we're getting a fixed group under an automorphism that is just a finite group. It can't be realized as a matrix group over FQ, but it is realized as the fixed points of an algebraic group over the algebraic closure of FP. At any rate, so this is a list of exceptional groups. So as I said, SC simply connected, add means adjoint. So these are types of simple algebraic groups. And then from this list, immediately G2Q and F4Q, well, G2Q when Q is greater than 2, these are simple. E8Q is simple. These Re groups are simple. And E7, well, if Q is even, then all of these groups turn out to be the same. Otherwise, and then here is the difference between the adjoint type and simply connected type. If Q is odd, then the adjoint type group has an index 2 simple group, E7Q. And when Q is odd, the simply connected, you can mod out by an order 2 center, and you get a simple group. So in other words, E7 simply connected is some cover of the simple group of type E7, and E7Q adjoint is some supergroup of, by index 2, of the simple group of type E7. So you can kind of think of these as playing the role of, say, PGL has a has the subgroup that is PSL, which is simple, and on the other hand, SL is a cover of, if you mod out by this number, PSL. So you can think of these PGL and SL are playing the role of adjoint and simply connected in the type A case. Okay, well, E6, here this has to do with mod 3 because there's an order 3 center in the simply connected case. And so, well, so E6 adjoint has an index 3 simple subgroup. Simply connected has an order 3 cover, is an order 3 cover of a simple subgroup. So this is just a classification. Twisted E6, it's the same situation as E6, except instead when you look at when Q is not -1 mod 3. Okay, so I'm a bit of a completist. I wanted to list these things. There's also a funny exception. This regroup when Q is just 2, this is not simple, but it has a index 2 derived subgroup called the Tietz group, which is simple. This is sometimes called the 27th sporadic group because it's technically not a group of Lie type. You're not getting it in the ways as we're getting it up here, but it is a finite simple group. I look at it as a finite simple group of Lie type. And as I mentioned before, the triality group, Steinberg triality group, this is considered an exceptional group. And we have these other B2, you can use an order 2 graph automorphism along with this other order 2 automorphism that's number theoretic. So these are called Suzuki groups. Okay, so that's just a list of exceptional groups. So here's what's known about these things. So first, due to work of Berry that I mentioned earlier, the Steinberg triality group is totally orthogonal. It's strongly real. This was one of the papers by this group of mathematicians in Siberia who went through a lot of these things and classified which ones were strongly real. So this is one of these lists of totally orthogonal finite simple groups. Okay, so these Suzuki groups, which I haven't said too much about, but they're relatively small. All the real classes are strongly real. This was actually explained by Suzuki in his original paper in the 50s or 60s. And a generic character table is given. You can check all real valued characters satisfy that they're indicators 1. Okay, what about twisted G2? Again, from in the paper of Ree, or possibly in a paper by someone else after Ree, a generic character table was given, and you can check all of the indicators are 1. And in fact, the Seeloff 2 subgroup of this Ree group is abelian. And that's listed in Ree's original paper. And that means from Gao, since all of the real valued characters are orthogonal, all of the real classes are strongly real. G2. Well, first, G2Q, now we're starting to get into more interesting business. Real valued characters all have indicator 1. This comes out of work of Omori and Enomoto, which was in the 90s. And our host, Anupam Singh, and his advisor, Manish Thakur, proved in 2008 that as long as Q is not divisible by 2 or 3, all of the real classes of G2Q are strongly real. Now, since then, we've had some time since then, and GAP has now incorporated a full generic character table of G2Q, which means we can just put in the character table of G2Q, that's all in terms of Q, and then we can compute these class multiplication coefficients that I mentioned in lecture 1, and we can see that, in fact, even when Q is a power of 2 or 3, all the classes of G2Q are strongly real. So this is now G2Q, some of these things are proved theoretically, and there's some other nice results from this paper of Singh and Thakur that we'll come back to later that are very useful. But now there's some computation power that's involved that we can check for these bad primes. Okay, so now what about this regroup? So we're increasing in rank now. Well, now we're at rank 4. This regroup of type F4. So first, Gunter Mahle computed that there's a unipotent character of this group, which is symplectic. So now we've got our first exceptional group where we have a character with indicator -1. And this is also the edge of computational knowledge in terms of generic character tables. There is a generic character table of this twisted F4. It's not completely implemented in GAP. However, if you contact the people who run GAP, they will help you with this. And I was able to compute with a colleague that this thing has 4 weakly real classes. So this twisted group of F4, it has a symplectic character, exactly 1, and it has 4 weakly real classes. And when Q is 2, this is the simple group. Well, this is just a single group. So this, just to mention it, we can actually completely just directly compute that these things, every real class is strongly real and every real valued character is orthogonal. Okay, so twisted F4, everything is behaving in this nice way. F4, this is where the computation power stops. The generic character table of F4 is not completely known. It's not implementable in GAP at the moment. Maybe it will be very soon. But all of the character degrees are known. So in a minute, I'll explain why for any of these finite simple groups of Lie type, well, you saw a classification in Professor Prasad's lectures, and we'll see why that can be used to just write down every character degree that you need of F4. So we can completely write down all the character degrees. The involutions of F4Q are also classified. There's papers where you can say precisely what the involution classes in each of these exceptional groups are. Well, so Meinhof-Geck in 2003 found that this group, so all of these unipotent characters of these things, essentially the indicators have been computed for the unipotent characters. The unipotent characters are a small subset of all of the characters, but they're very, very much a guiding factor in the construction of all characters. But the point is, Geck has computed that there are 4 characters which are not real valued, that are unipotent. And as it turns out, and I felt very lucky when this happened, a postdoc that is a colleague of mine and I did a computation. What we did is we said, okay, this thing has 4 unipotent characters which are not real valued. We took every other character degree other than these 4 characters, and we summed all of them. We can find the degrees, we can sum them. That turns out to be equal to the number of involutions. So you just sum up all the other character degrees other than these 4, and you compare it to the number of involutions, and they're equal by almost a miracle. These are the only 4 characters which are not real valued. The rest are real valued, and by the Farbini-Schur involution count from last time, because the character degree sum of the real valued characters is equal to the number of involutions, all of the real valued characters of F4 are orthogonal. So this was computed. Stephen Trefethen is a postdoc at William and Mary that I've been working with on some of this stuff. So, okay, now all real valued characters of F4 have indicator 1. So this is now known. And now we get to our first open problem in this direction, and that's prove that all real classes of F4Q are strongly real. This is open. It would be great if one of you proved this. I would love it. And this is where the information on F4 stops. So in fact, while I'll now tell you more about information on the indicators of characters of these exceptional groups, I don't know any more about the classes. Somehow the classes, there's so much known about the characters in terms of their parameterization and their degrees that we can say quite a lot about them. The classes and which ones are real, whether those are strongly real, this seems to be harder with the present state of knowledge. So if you can do this for F4, this would be a fantastic result. Okay, so what's remaining? The remaining simple exceptional groups.
Ryan, just to
Yes,
follow up on this open problem,
yes.
I mean, for semi-simple classes, there is no problem.
Semi-simple classes, it's very well known. Yes, in fact, this will come up later. So the fact that we know a lot about semi-simple classes actually helps us with the characters. But knowing about the semi-simple classes is not enough to say everything about all of the classes, but it's a great starting point. So yes, semi-simple classes of F4, it's known that they are real. And in fact, I think maybe in that same paper of Singh and Thacker, it was proved that all the semi-simple classes are strongly real. Anupam,
yeah, I can imagine that, because anyway, it's a calculation. Basically, the point is that the -1 is there in the while group, and that is all that you need to prove that real classes are strongly real.
Well, that's all you need for the semi-simple.
Semi-simple,
classes.
yeah,
Yes,
semi-simple.
yes.
Semi-simple, but then cannot you go a little further and look at centralizer of semi-simple elements?
Well, I invite anyone to go through that calculation, but it gets hard. It gets hard.
What is the situation for unipotent ones?
Unknown.
Unipotent, you don't know?
I don't know.
One knows how many of them are there, because there are 4 of them which are not real.
There are 4 unipotent characters, but one would have that are not real. But there's not necessarily a direct correspondence to unipotent classes being not real in that case. One has to be a little careful there.
Okay, but how many of them are there? How many unipotent representations are there?
I don't know off the top of my head, to be honest.
Okay.
Yeah.
Right.
Yeah. But there are more problems here. More problems. So there are questions to be answered here, and there are things to work with. So certainly this is not a problem that is out of reach, and there are starting points. And I've worked on it some, but I haven't managed to get a full answer here. But it certainly is a doable problem. Yeah. So what about these remaining exceptional groups? So now this is actually exactly what Debendra was talking about. Knowing something about the semi-simple classes will tell us a lot, and it tells us a lot through the Jordan decomposition of characters. So let me remind you what the Jordan decomposition of characters is, which is essentially Lustig's parameterization of all of the irreducible characters of these groups. So here's a general setup. If we have a connected reductive group, so it's defined over some algebraic closure of a finite field, And let's assume, for simplicity's sake, that it has connected center. Then we have some Lie dual group and some dual Frobenius map. So this dual group depends just on the type of G, and then you can say what the type of G star is. And then we have the fixed points under these Frobenius maps. So now let's look at a semi-simple class in the dual group and this script E parameterized by the semi-simple class S. This is a subset of the irreducible classes of our finite reductive group called the Lustig series. And these things partition all of the irreducible characters as S ranges over all of the semi-simple classes in the dual group G star. So the Jordan decomposition map, first it's a bijection, and I'm just calling it JS. Bijection from the Lustig series to the centralizer, so the unipotent characters of the centralizer of that semi-simple element in the dual group. So we're kind of almost kind of a deflation down to just unipotent characters, but of the centralizer in the dual group. So it's parameterized by a semi-simple class in the dual group. You look at the centralizer of that semi-simple class. You look at the unipotent characters. So there's a unipotent character here that corresponds bijectively to the irreducible character in this Lustig series. And this map has a lot of properties. There's some extremely important properties. There's an inner product property, which I won't mention because we don't particularly need it, but it's very much a guiding property. And it's an important property in terms of how Lustig classified all the irreducible characters. But one of the important properties that we need is that one can tell the character degree, and this is what I was mentioning earlier. We can write down all of the character degrees of these things as long as semi-simple classes are classified. And the character degree corresponding to chi in this Lustig series is given by the following expression. It is the degree of the corresponding unipotent character. So if you know the degrees of unipotent characters, you can compute this, times not the index of the centralizer, but rather the p prime part of the index of the centralizer. So now the point is that Lustig computed a massive computation, computed all of the degrees of all of the unipotent characters of all of these types of finite groups of Lie type. These have all been computed. Thank you to Lustig. So these things are known, which means if you know all of the semi-simple classes, you find their centralizers, you know the type, then thanks to Lustig, you can write down all of the character degrees of these, which means you can then write down all of the character degrees in this Lustig series.
Can I just interrupt?
Of course.
When you say Lustig computed,
yes,
there is some formula for psi1 which you gave for GLN last time in terms of hook length.
Yes.
And somehow hook length is the dimension of the representation of the Weil group. So
yes,
there is some similar formulae in all cases. So it's not too much case by case.
I will say similar is too strong of a word there. So it gets extremely complicated, and in terms of this association between unipotent characters and Weil group, and it's something I don't understand. It's something where this is where character sheaves come in, and the structure gets incredibly more complicated somehow when you leave the type A case, and it's not so clear how this correspondence between the combinatorics of the Weil group and the dimension of the unipotent representation correspond. It somehow gets extremely complicated. In type A, we have this extremely tight control over the character degree by understanding just the symmetric group. But somehow this isn't so tight in the other cases, and it's something I don't understand.
At least for classical group, it must be the case. At least for classical groups.
Classical group, we will get into that, but in fact, the combinatorial control is not so clear.
Oh.
Yeah, so this is something that's not so clear. I mean, there is a one can write down some nice bijection, but in terms of the and there is a nice formula for unipotent character degrees in terms of these combinatorial objects that Lustig invents called symbols.
Yeah.
And in fact, one can write down those character degrees in terms of something that one can define. So some work in the 80s, some people managed to write down what a hook length should be for a symbol and managed to write down the character degree in terms of what are defined as hook lengths of symbols. However, the missing part is whether one can write down those character degrees as values of some symmetric function, which is one more step that we used last time in order to make these computations. So in the type A case, not only do you have a hook length formula, but you can correspond that to the value of some Schur function, some Schur symmetric function. And then there's a lot of computation power. But there's this missing bridge, and I'm going to address that. And I'm going to give some evidence that it should be there and it shouldn't be, but no one has written this down. So these are all questions that I am looking for answers for. And so I'm glad you asked them, because these are going to be key questions that are going to come up later. So, but something you pointed out last time, not everything is answered here. There are a lot of answers for finite groups of Lie type, and there are a lot of still open questions in terms of structure. Okay, so this Jordan decomposition map, here's something in terms of structure. So this comes from Dean and Michel in a 1990 paper, showed that when the center of our overlying algebraic group is connected, then there's a unique Jordan decomposition map with respect to a list of properties. And using this result, Bama Srinivasan and I in 2015 proved the following result. And the result is essentially complex conjugation behaves well over this Jordan decomposition map. So if you have a character chi that is mapped to a unipotent character psi under this bijection, and you look at the complex conjugate, well, one, this isn't so hard to show. It's in the Lustig series that's determined by the semi-simple class of S inverse. But then what's harder to show is that this chi bar is always mapped to the complex conjugate of psi. So this feature of the Jordan decomposition map had not been known up to 2015. So here's an example of some structure that was not known before this. In fact, and a little later, 2020, Bama Srinivasan and I managed to generalize this to account for any Galois automorphism. So if one takes any Galois action on the character values, then one can describe the behavior under the Jordan decomposition map. However, I want to point out connected center, G having connected center is a crucial crucial feature of the conditions here. So this is a guiding geometric condition that gives a lot of nicer properties for finite reductive groups. Okay, so the point is that we can then read off what real valued characters are. If we know the Jordan decomposition, we can say, okay, this means that we have a character, if it has Jordan decomposition, given by this class of pairs. So S is a semi-simple class, so if we conjugate S, we're conjugating the corresponding unipotent character. So if this class of pairs is conjugate in the dual group to the class of pairs S inverse, comma, psi bar, then that corresponds to a real valued character. So, and now what can we say? Well, in the same paper of Singh and Thacker, which was mentioned earlier, all of the semi-simple classes in type E7 and E8 are real. So this is something that Dipendra mentioned earlier. So for some of these groups, when you have -1 in the vial group, this is enough to say very useful information about the semi-simple classes. And the fact that all of the semi-simple classes are real here allows us to say something here. Well, S is always conjugate to S inverse. And that allows us to go through. So why am I taking E7 adjoint type? This is because this comes from a connected center type group. E8, always trivial center. Somehow E8 is the most cooperative of groups in these computations. So we know the character degrees of all of these groups, and we can use this result on the real valued characters and the fact that all of the semi-simple classes are real. So S is always conjugate to S inverse. We can use that and results of Geck on fields of character values of unipotent characters to write down specific characters which are not real valued. So what I'm trying to do here is say, okay, in F4, only 4 characters are not real valued and they were all unipotent. There are more characters which are not real valued here, but we can produce them using this information. We can piece this information together to construct a lot of real valued irreducible, non-real valued irreducible characters. And what we were able to do is then sum the degrees of the rest of the characters. So we produced a bunch of non-real valued characters until we suspected this must be all of them. And we confirmed they were all of them because when we sum the other character degrees, we get exactly the number of involutions in both of these groups. So this is a result of, again, this postdoc Stephen Trefethen and I published in 2020. For either of these groups, either E7 of adjoint type or E8, every real valued character is orthogonal. So we have this nice behavior for these groups. And this is quite a big computation. There are quite a few tables in this. This is a very computational proof. However, it uses very crucially this result on real valued characters and the Jordan decomposition, along with this key result that every semi-simple class is real in these type groups. Okay, well, so what's the problem with the other groups? E7 simply connected, it does not have a connected center. It has order 2. So we don't have enough information on the Jordan decomposition map. But we've made some computations. It seems like...
Ryan, can I just
Yes.
go back to this theorem?
Of course.
Eventually, it's the same strategy that you count the dimension of the representations and count the involutions.
Correct. Yes.
That's a lot of work. I mean,
it is quite a lot of work. However, these computing packages like GAP have amazing power at this point. And luckily, this postdoc, Stephen Trefethen, he's very, very good at computation. And you know, there's this whole school of computational representation theorists who are developing GAP and all this. Yeah, it's amazing to me, but this is all. This can all be calculated. Yeah.
I don't see how one can even calculate number of involutions.
This is old. These are old results from the. I'll send you our paper, which has a lot of references. But these were all computed in the 80s. So in fact, there are papers, and it had to do with I think in the classification of finite simple groups, a lot of things have to do with involutions and centralizers of involutions. And so there was
known already.
Already known. Already known. Correct.
But then you have to match it with the sum of the degrees, and
correct. And
my
magic
God.
happens. It works. It works. Yeah.
I see.
Although this actually maybe I will what I'm going to do, let me just show you, because I find it to be of course it's work I worked on. Of course I find it interesting. However, I'm going to just share with you the tables that come up in this a tab. So here's this paper where I'm basically giving a summary of this paper now. However, this is all these polynomials in Q. So here, there's this list. I mean, just to show you the amount of computation that was needed, here's a table of all of the non-real valued characters in E8.
My God.
And yes. So these are all the characters the character degrees in terms of cyclotomic polynomials. And this is the number of them.
Valued.
Yeah,
So
non-real valued.
Non-self-dual.
Yes, non-self-dual. And E7, significantly smaller list. E7. But the point is that we have the number of involutions. So here's a table. So these are all known. And so, yeah, a big computation, but completely classifiable. So, yeah, big computation.
For E8, most of the representations are self-dual.
Most are, yes. And so we have an exact count. In fact, let me find the precise statement, which I didn't give in my handwritten notes. So E8, yes. So there's exactly, well, we have polynomials in Q for exactly the number which are not real valued.
Number of irreducible characters which are not real valued is 2Q square. So this is a very small set.
This is small compared to the size of E8, yes.
I mean,
This
E8 is kind of horrendously large.
Yeah, I mean, you have some big, just the sum of the degrees is some...
Ryan, I have the feeling that you should be able to do better. No, I mean, it's a very small set. You can classify them?
Oh, the non-real valued characters?
Yeah.
Yeah. The table, I gave you the table. They're completely classified.
But that is table by computation. But I'm saying that once the table is there, you can prove an abstract theorem that, no?
No, we did. No, the table is there. So we found the non-real valued characters using Jordan decomposition.
Okay.
Well, but then we had to confirm they were the only ones. So we were able to produce a lot of non-real valued characters using exactly this Jordan decomposition statement. But then what we had to do is confirm that they were the only ones that were there. And by doing that, we got for free that all of the indicators are 1 for the self-dual.
Am I right to assume that if one was doing this Jordan decomposition for E8, you will be looking at centralizer of semi-simple elements, and they are all known, and
yes,
one
exactly.
knows how many of the unipotent representations of those centralizers are real valued?
Yes, exactly. This is exactly the process. Okay. This is exactly the process. Correct.
One knows all the centralizers in E8?
Yes. Yes. These are all classified, all written down.
By whom?
Oh gosh. So there's 50 references in that paper. And we gave all of the historical references for all of this stuff.
All right, good.
But it is, yeah, I will send a copy of that paper so that that can be posted as well. But yeah. So, okay, so the exceptional groups, I mean, there are interesting things going on. E7 simply connected, we strongly suspect that a self-dual character is orthogonal if and only if the central character is trivial, much like the symplectic group. And what we're missing here is a little information about the Jordan decomposition map, because the center is disconnected. And there you need more information on action by automorphisms on the Jordan decomposition map, but we're almost there. So this is something we're working on, and we're there. And if we prove this about E7 simply connected, then as a corollary, we get that all real value characters of the simple group E7Q are orthogonal. So we're almost there. For E6, now here's another open problem, which is very doable. We just haven't done it yet. We haven't been able to. E6, the Weil group does not contain -1. And this means that not all semisimple classes are real. And there is no classification of real semisimple classes of E6. Part of this has to do with how the semisimple classes are classified. I tried to understand how one might read off when the semisimple classes are real, but I don't understand how. I've asked a few people how one might do this, classify the real semisimple classes of E6, either standard or twisted. And it just hasn't been done. So this is a problem. Again, very doable. And if we knew what the real semisimple classes of E6 were, then we could conjecture that everything else outside of those semisimple classes, outside of those Lustig series, might be not real valued. And then there, E6 has a lot of characters which are not real valued, unlike E7 and E8. And it's because of this fact, -1 is not in the Weil group. Real semisimple classes are not necessarily real. And in fact, it doesn't seem, not a majority of them are real, I would say. Maybe a majority, maybe not a strong majority. In other words, something's funny with E6 in that, unlike E7 and E8, most of the characters are self-dual. That may not be the case for E6.
I mean, just to say that, this trick that you use of GLN extended to GLN plus.
Yes. Yes.
That trick is available for E6.
It is. Although...
And that might make all the class, it may have the same...
Yes, I agree. But there's a problem here, is another problem hiding. So E6, so if you look at GL, this is some cover of the adjoint type group, PGL. And it's helpful that GL has connected center. However, E6 does not have connected center. So I think and I thought of exactly what you're saying, right? So we want something where twisted indicators might be 1, and we can get totally orthogonal. But we have to make the center connected first. So we have to tack on some connectedness to the center to glue that together, and then tack on top of that in order to automorphism, that is the graph automorphism. But yes, I agree completely. All of that should be true, but there's a little more geometry to worry about, unfortunately.
Mm-hmm.
But yeah, that connection should be there. This graph automorphism should play the exact same role. And in fact, what I'm going to talk about next is in the orthogonal group, there's also a graph automorphism.
Yes.
And this will play an important role. So I'm just going, for the exceptional groups, I'm going to stop here by saying, letting you know that it has been found, Omori computed that the twisted E6 does have symplectic characters. It's unknown how many. Weakly real classes of twisted E6 have not been written down. Maybe there's a weakly real semisimple class. I'm not sure. I wouldn't be surprised. But this is what's known about the exceptional groups, and there are a couple problems here that maybe some of you can solve. So exceptional groups will leave for now. Okay, so now symplectic and orthogonal groups. So I'm just going to give you an outline of what's going on here. So Gao, as I've mentioned several times, when Q's odd, all of these special orthogonal groups and orthogonal groups are totally orthogonal. And when you have dimension 4 and plus 2, all of the real value characters are orthogonal. And then when Q is odd, any real value character of the symplectic group is orthogonal. Well, if and only if the central character is trivial. So just to remind you of that. But it is known. Oh, my light's blinking here. It is known that when Q is even or odd, the orthogonal group is strongly real. So this was accomplished by Wonenberger in 1966 for Q odd, and Gao when Q is even. He proved this. And the special orthogonal group for dimension 4m is strongly real. Again, Wonenberger when Q is odd, along with Neupel and Thompson in 1998 kind of fixed some errors of Wonenberger and extended some things. And when Q is even, this I mentioned, this is a Finnish mathematician, Joanna Ramo, in 2011 proved that when Q is even, these things are strongly real. And also I wanted to point out, when Q is even, the special orthogonal group of even dimension is simple. It's the same as this omega, this simple orthogonal group. That's when Q is even. When Q is even, also, it's known that the symplectic group is strongly real. This is in the same paper of Gao in 1991.
Just, I get confused about SO2n Q even. How do you define this group?
So one can define for any Q the orthogonal group to be the stabilizer of a split quadratic form over the algebraic closure. And this thing is disconnected. The connected component can be defined to be the special orthogonal group.
No, but can one just take it to be the anti-diagonal one?
Anti-diagonal one can define the quadratic form. However, there are some things to get around when Q is even. And the way gets... I'm sorry?
That's what I'm asking, because...
Yeah. And that's what I'm answering. So when it doesn't matter what Q is, one can define the orthogonal group to be the split orthogonal group to be the over an algebraic closure to be exactly the stabilizer of the quadratic form you stated. And then one can look at fixed points for the finite orthogonal group, except on the algebraic group level, one defines for any Q the special orthogonal group to be the connected component of the orthogonal group.
No, but you see, the problem is that that anti-diagonal defines you the symplectic group in Q equals 2.
But I'm not defining it in terms of a bilinear form. I'm defining it in terms of quadratic form, and that's different. That's what you have to get around.
So it's not defined by A J A transpose equal to J.
Well, one defines it in terms of a quadratic form. So yeah, the confusion is when the quadratic forms correspond to symmetric forms when Q is odd, and this is not the case when Q is even. So we threw away the bilinear form when actually, if one wants to do it universally, we just throw away the bilinear form. And instead, we just define the quadratic form. But the quadratic form defines the orthogonal group, whether Q is even or odd.
So it's not defined in such a simple way as A J A transpose is equal to J.
Correct. It's not defined in that case when Q is even. It can't be. Yeah. So we have to go back to just the quadratic form rather than the bilinear form, which corresponds to the quadratic form in the Q odd case.
That will be more complicated to define than the orthogonal group.
It is a bit, but it is a bit more complicated, but it can be done universally.
Okay. All right. Thanks.
Yeah, sure. Of course. So here's a key fact. A key fact in terms of these things. When Q is a power of 2, in fact, this symplectic group is isomorphic to the special orthogonal group with odd dimension. So this is a very good question in terms of how to define these things. And in fact, I almost had a slide going through the construction, but then realized I would run out of time if I had a full slide doing that. But I do this in the paper corresponding to this. So I can, in fact, I'll also send you this paper and refer you to the section where one can construct these things universally, independent of Q. So this is a key fact. When Q is a power of 2, these two groups are isomorphic. The symplectic group and the special orthogonal group of odd dimension.
Which also means that SO2n sits inside sp2n, I suppose. Because SO2n sits inside SO2n plus 1.
Yes.
So it sits inside sp2n. So, this question I asked about A transpose J, A equals J. So it is, it certainly is contained there, which defines you the symplectic group, but it is somewhat smaller, and maybe it can be said more quickly. I don't know. It's just a stabilizer of a point, but in SO2n plus 1. Yeah.
Yes. So another important fact is that no matter what your Q is, so this is a fact about algebraic groups, the Lie dual group of the symplectic group is the special orthogonal group. So symplectic group of odd dimension. So the symplectic group and the special orthogonal group of odd dimension are connected in this crucial way. And also when Q is even, what that gives us, since we have this nice isomorphism, the symplectic group, when Q is even, is somehow Lie self-dual, much like GLN is. GLN is its own dual group in terms of the Lie dual. The special orthogonal group for any Q is also its own Lie dual. G star and G are the same group. And here's the main strategy. So this is the outline for showing that these things are totally orthogonal. So the orthogonal group when Q is even, symplectic group when Q is even, all of these things. So it's a similar thing, except now we have, instead of exceptional groups, we can just sum the degrees. We can look at the involutions. Here we have, of course, an infinite series of groups. So we construct a generating function for the character degree sum. And we want to compare it to generating functions for the number of involutions. So these are also already known. The numbers of involutions in these groups, generating functions have been written down. And in the other course in this workshop, you're looking at other powers, I know. But so for involutions, there's a paper of Fullman, Grolnick, and Stanton from 2017. And then a student of mine, Greg Taylor, and I wrote down the other generating functions for involutions for a few cases that were not written down there. So this is the main strategy. We want to write down generating functions for the character degree sum. Okay, but of course, this isn't easy, and there's an obstruction. And this comes up to a question earlier. So the obstruction comes when we want to sum the unipotent character degrees for the special orthogonal group. So the special orthogonal group are all of these dual groups, either of odd dimension or even dimension. And when we try to sum the unipotent character degrees, we don't have a way of coming up with a nice generating function that can be manipulated because the values of exactly what I was saying before, the values of these unipotent character degrees, while there's a formula for them, they have not been interpreted as values of some nice symmetric functions, which is how one manipulates these infinite Q series. There are all these nice identities for symmetric functions that one can write down essentially from understanding the combinatorics of the symmetric group well, or generalizations of the symmetric group. So this is something that would be needed if one wanted to manipulate these unipotent character degree sums directly as some nice interpretation for these character degrees as values of symmetric functions. This is still open. So I tried to do this. This seems hard, and I'm still working on it. However was first. Now is but. We can get around this. How do we get around this obstruction? Well, when Q is odd, we know what we're trying to prove is true. We know from Gau's work And I pointed out last time why it only works when Q is odd. So the point is, when Q is odd, we actually get an identity. We get this character degree sum on one side is equal to the number of involutions on the other. And the point is that this missing identity for the sum of the unipotent character degrees, which we couldn't get directly, we can solve for it from this identity when Q is odd. And here's a key fact that I mentioned last time, which follows from Lustig's work. If you have a finite reductive group over this finite field of Q elements, and you look at the character degrees of the unipotents, those things are polynomials in Q which do not change when you change Q. So you parameterize the unipotent characters, and based on each unipotent, you have a character degree which is a polynomial in Q which is invariant when you change Q. So in other words, the sum of unipotent character degrees is invariant whether Q is even or odd. So this means from this step 3, when we solve for this missing identity, we can get an identity that's true for any Q using this key fact. Then we substitute it into our character degree sum we tried to compute before, and what pops out is exactly the number of involutions. And so it's still evaluating a character degree sum, identifying it with the number of involutions, but there is some complication here. But here's a bonus which we get out of this. What we get out, and I'll give a few details, what we get out are new Q-series identities for sums of character degrees of unipotent characters for symplectic and orthogonal groups, which look to be some kind of symmetric function type thing, which still working on why. Okay, so here are just some details, which I won't spend too much time on, because well, one, too many details of this calculation maybe are boring, but here is the gist of it. So when we look at the symplectic group, well, the dual group is SO2n plus 1. And what we're going to do is just calculate the character degree sum of SO2n plus 1, because when Q is even, that's the same as SP2nQ. And when Q is odd, we know it's equal to the number of involutions. So when we compute the character degree sum for SO2n plus 1Q, the dual group is SP2n, and we know that SO2n plus 1 is connected with connected center, and so we can use directly the Jordan decomposition of characters, and we can classify centralizers of semisimple elements in SP. And it turns out all of the centralizers look as follows. They're a product of GLNs, a product of unitaries, and then depending on whether that semisimple class has 1 or minus 1 eigenvalues, we get a couple of symplectic factors. And then a unipotent character of such a centralizer is just a product of unipotent characters. So we get some unipotent characters of GL, which have a hook length formula, as we saw last time. Unipotent characters of the unitary group, I haven't said too much about this because, well, it's almost another topic. We also have hook length characters for these unipotent characters by changing Q's into minus Q's. So the point is that we have hook length formulas for the character degree sums of these, which are then values of symmetric functions. So the resulting things that we get for the character degree sum are completely manipulatable for the GL and U factors. But these symplectic factors, this is where we have a mystery factor. So when we write down the generating function, we get something not too different than what we saw last time, except we have these nice sure function identities for GL factors and U factors. Then we have this mystery symplectic factor. Well, it is a power to 1 or 2 because When Q is odd, we could have 1 or -1 eigenvalues. When Q is even, we could only have 1 eigenvalues. -1 isn't there. So this mystery factor appears to a power of 1 or 2, depending on when Q is even or odd. And what happens is we go through the process that I said before. We know that this generating function is the number of involutions when Q is odd, and we can solve for the mystery factor and plug it back in, and we get this nice, this is the identity we get. We get the sum of the degrees of the unipotent characters of either the symplectic group or the special orthogonal group for odd dimension is this factor, so some Q factor, times the coefficient in the expansion of this product. So one of the things I'm working on is how to get a direct combinatorial proof of this, and this will reveal a better answer for the character degrees of these things in terms of not only hook lengths, but in terms of values of symmetric functions, which is a deeper combinatorial structure of these things. Okay, so what about the orthogonal and special orthogonal groups? So there's more obstructions here. And here is a key part. So the algebraic group that is the orthogonal group of even dimension, this thing is disconnected. And so this is what I was mentioning before. The one way you can define SO2n universally is just look at this group defined by a quadratic form, look at the connected component, and then look at fixed points of that algebraic group. But even though this is disconnected, it turns out there is still a Jordan decomposition map of characters for the finite orthogonal group. However, this thing depends on what is a deep fact, that there's a Jordan decomposition map of the special orthogonal group, which comes from a disconnected center. So even there's a problem. But that is invariant under the graph automorphism of the special orthogonal group. So this was a problem that I realized when I was trying to make this computation, but Jay Taylor and Mandy Schaefer-Fry wrote a paper in which they were able to clarify this. And this seems to be some deep fact about Jordan decomposition maps and commutation with automorphisms that come from the algebraic group. So this is one problem that has to be solved, and it is. But then the centralizers of semi-simple elements in SO, these things are disconnected. So then there's another, and so there's a lot of index 2 bookkeeping to be done. And another thing that turns out to be easier in terms of counting, if one considers both the split and non-split special orthogonal groups at the same time, that is, we look at the character degree sum of these at the same time, and the and the number of involutions in these at the same time, that is the number of involutions in either group, this has a better combinatorial form. And so in the end, what we get as a bonus result is that for the 4m+2 dimension, if iota is the order 2 graph automorphism, which can be defined as an inner automorphism on the orthogonal group, but is an outer automorphism of the special orthogonal group, all of the twisted indicators corresponding to that graph automorphism are 1 for this dimension. So one of the things that's happening here, the full orthogonal group is obtained by adjoining the graph automorphism of the special orthogonal group. And in some ways, this full orthogonal group is playing the role of the general linear group when you put in the inverse transpose automorphism. And indeed, the full orthogonal group is totally orthogonal, like the general linear group with inverse transpose put in. The weird thing about this is that this graph automorphism has twisted indicators all 1 only in the 4m+2 case. Not in the 4m case. There, all of the standard indicators are 1. but the twisted indicators are 0 or 1. So this switching between 4m and 4m plus 2 gives this interesting structure. Oh, right. I should also say that for the unitary group, if one considers the inverse transpose automorphism, all of the twisted indicators are 1 for this group. This is a result of Nat Thiem and myself. Most of this work actually was done when I was a postdoc at TIFR in 2004, 2005, and the paper was published in 2007. So now what we get, and this, I mean, one must manipulate the character degrees in some way to say what we mean by unipotent characters of the orthogonal group. But there's a certain modified character degree sum for unipotent characters of these things. That's the coefficient of this nice Q-series infinite product. So this one is very similar to the one for the symplectic group. There's only a sign change. I think this plus, oh, no. There's an exponent change. This 2i changes to a 2i minus 1 here. And other than that, it's the same. So there's some crucial combinatorics that is hidden underneath all of this that I'm still trying to learn. Okay, so these are just the highlights of this proof for Q even, but what we get is a better picture of what's going on for Q even or odd, and we get this key this in this orthogonal case, this key fact about the graph automorphism, which I think is a crucial piece to all of this. Okay, so these are basically, this talk is just all of the things I know about these things, and the things I'm not saying, well, it's probably because I don't know the answer. There are a lot of questions here. But I'd like to finish with a general conjecture and to give some general result first that gives motivation for a general conjecture. So this is a result of Dipendra-Prasad on groups of Lie type in general and indicators. So this is a nice general result for a certain class of characters. And this comes to the Gelfand-Graev representation. So if you take a maximal unipotent subgroup of a finite reductive group, and you take a linear character of that unipotent subgroup that is so-called non-degenerate, and geometrically that means it non-trivially acts on the root spaces corresponding to our unipotent subgroup. If you induce that linear character, you get a representation which is always multiplicity-free. This is the Gelfand-Graev representation. And first noted that this was multiplicity-free by Gelfand and Graev, hence the name. Steinberg went back and proved that this is always multiplicity-free no matter what type of group. And the characters that appear with multiplicity 1 in here, these have a few names. They're called regular characters. They're called generic characters in the p-adic sense. This has plays a very important role in the representation of p-adic groups. But here's the result. So if this thing has, so there's a bigger result, but this is the most general thing that we can say that always happens. So if G has connected center, then there is always a central element that guides whether a real valued regular character has 1 or minus 1 indicator. So the value of the central character at that central element is either 1 or minus 1, and it tells us whether the indicator is 1 or minus 1. So this is a very nice result, very structural result, tells us something key about the geometry guiding these indicators. And this is specifically for these characters appearing in the Gelfand-Graev representation. Now, geometrically, we can extend this property to some other characters. So there's something called the Alvis-Curtis duality on irreducible characters of finite reductive groups, which is an order 2 isometry. One can think of this combinatorially for Sn if one transposes the diagrams of partitions, then this gives an order 2 isometry on the characters of the symmetric group. Alvis-Curtis duality is some kind of extension of this map. But one result is that the Frobenius-Schur indicator is invariant under Alvis-Curtis duality. That's something I managed to prove in 2010. And the duals of these characters in the Gelfand-Graev representation are called semi-simple characters. Most of the time, they have character degree, which is prime to the underlying characteristic P. But more importantly, they're always parameterized in this way by the Jordan decomposition. Just a semi-simple character, a semi-simple class in the dual group, and the unipotent character is just the trivial character here. So these are always the semi-simple character parameterizations in the Jordan decomposition. And so through this result, one gives a start of how the Frobenius-Schur indicator might guide how the Jordan decomposition might guide the Frobenius-Schur indicators of characters in general. I wanted to make this quick note. So one might hope that you can extend these Gelfand-Graev characters to get every character. And one can do this for GLN. So there are these more general constructions called degenerate Gelfand-Graev representations. Even more general are something called generalized Gelfand-Graev representations. And in the general case, you cannot get information about every character. You lose a lot of information. But for GLN, this gives a very nice proof that every real valued character has indicator 1. And for many cases of SLN, but not every case of SLN. But it doesn't give you the twisted indicators for GLN. But so there is a way to extend this method to, well, GLNQ at least, type A things. But for general type, it gets messy. So I'd like to now just finish with a few conjectures. And one of the things I'd like to notice is if you take a group of adjoint type, an adjoint type simple algebraic group always has trivial center. So what this result of Prasad says that is if G is a simple algebraic group of adjoint type, then every self-dual generic character is orthogonal because there's only one central element. And the fact that all of the fact that all of these things, all of the self-dual characters are orthogonal in this case, well, it seems like the only time these things get broken is when the center is disconnected. So somehow there's a cohomological variance that allows -1 indicators sometimes, or if our Frobenius map is twisted. So if it's not a standard Frobenius map, but it's twisted by some automorphism, for example, in the twisted E6 case, we get -1 indicators. But so here's a general conjecture. So if we have a connected reductive group and it has connected center, and we take a standard untwisted Frobenius map, then the resulting finite reductive group, I believe all the real classes should be strongly real, and all of the real valued characters should be orthogonal. So these should be the two guiding geometric conditions and a kind of a number theoretic condition. The Frobenius map is not twisted. And more generally, so if we look at some other groups, there are, of course, other groups we can look at. SLN I didn't say much about, but if we look at that, everything is known about the real classes. Again, some results of Anupam Singh and Nick Gill classify the strongly real classes of SLN. And in fact, one can see that all of the characters of SLN are orthogonal. Sorry, all of the real valued characters of SLN are orthogonal if and only if all of the real classes are strongly real. This comes out of that. But this is a more general conjecture. So if we have any connected reductive group and any Frobenius endomorphism, making it a finite group of Lie type, whether it's twisted or untwisted, I believe that this resulting finite group should have symplectic characters if and only if the finite group G has weakly real classes. So these are kind of my life goals now to prove these things. And so I've gone over a few minutes. So I will stop here with these conjectures.
Thank you, Ryan. It was really interesting and informative lecture. Thank you very much.
Thank you.
Yeah.
Brilliant. Very good.
Oh, thank you.
Yeah.
Thank you.
We can ask questions.
Can you say about the first conjecture on this page? Is it true for exceptional groups G2, F4, and E8?
So one of the things that we can say is that for if we ignore the all real classes are strongly real. So that like I said, F4, it's doable. I haven't done it yet. I believe it to be true, but it's true for G2. It's true. The real classes are strongly real. I don't know how to get at them for E8. So the things that I know most about now is that all of the real valued chi are orthogonal for G2, F4, E8, E7 adjoint type. So this is true. I expect it to be true for E6 adjoint type. So this part that all strongly real classes are all real valued characters are orthogonal, I feel like I'm actually quite close to this statement. The real classes are strongly real. This part I know less about.
So in terms of representations, the real valued characters are orthogonal, you know, for G2?
G2, F4, E7 of adjoint type, and E8.
So which group you don't know?
E6 adjoint type. I don't know E6. Let's see. Of course, that has, adjoint type. I don't know for E6. And those are the simple types. But then there is a whole structural question about if you have a connected reductive group with connected center, how is this related to geometrically with the underlying simple factors of adjoint type? So there's something called the adjoint projection map on algebraic groups, and I'm trying to understand how the Frobenius-Schur indicator carries through that map. So then one can take the simple groups of adjoint type and build out of it a statement, a general statement for connected reductive groups with connected center in general. But this is some structural question about how one puts together these groups from the simple type groups.
Mm-hmm. You said something about UN.
Yes.
One can construct the GLN plus analog of UN. And are the representations known to be self-dual for this group?
No, in fact, they're known to not be. There are characters which are not self-dual, and it's not orthogonal, totally orthogonal. So they're things
semi-direct product of UN by, so to say, complex conjugation, meaning UN has a.
Wait. Let's see. So I know that it's not totally orthogonal. That's right. So semi-direct product. So you take unitary group, you throw an inverse transpose. So this thing is not totally orthogonal. And the
but
fact
self-dual.
I have to think about that before answering that with confidence. But it's certainly true that I don't know off the top of my head. I'll have to think about that. I ran out of coffee.
I mean, I was proposing this also for E6.
Yes, that's right. That's right. Now for standard E6, I do believe that if you tack on a connected center and then throw in the graph automorphism, that this thing I think should be totally orthogonal. But the twisted E6, then the twists make things funny. So what happens with the unitary group, the twisted indicators corresponding to the inverse transpose are still all 1 for the unitary group. But for this group that's upstairs, unitary group with inverse transpose thrown in, I know for a fact it's not totally orthogonal. It might be self-dual. And as I said, I can't place my finger on a quick reason why that should be true. So I might have to get back to you on that one, Dipendra.
All right, good. I'm sorry, Anupam, can I ask some more questions? Anupam?
Yeah, of course. Let's just thank Ryan,
also,
and if somebody wants to leave, they can leave, and we can continue
but
discussing.
Others can also ask.
Just thank you.
Maybe,
Sure.
Yes, of course.
Yeah, thanks.
Maybe others can ask.
Thank you.
Yeah.
No,
yeah, we can continue
please
discussing. Yeah, you go ahead.
I wanted to ask about yesterday's lecture. You said that the sum of the dimension is the number of symmetric matrices.
Yes.
In mathematics, when two things are equal, usually there is more to it than just equal.
Yes.
So it would be best if, the sum of representations somehow appears on the other side.
Yes. In fact, what I do have an idea for how to one might get some combinatorial correspondence. So, in the symmetric group, one can make a realization between the character degree sum and the number of involutions through this thing called the Robinson-Shinstead correspondence. And one can count pairs of 10.
My suggestion was that, the GLN operates on the space of symmetric matrices.
Oh, that's true.
And you analyzed this yesterday. It is GLN upon ON plus and ON minus.
Yes.
So my question is whether the sum of these two representations, is it a Gelfand model?
It is not. Unfortunately. Never. Yeah.
But how far is it from being Gelfand?
It is quite far. There's lots of intersection. It just falls apart, unfortunately. This was actually the first question when I started my PhD thesis. This was the very first thing I tried. And I showed that it's never a Gelfand model. There's way too much intersection. It just isn't there, unfortunately.
The two objects, they interfere with each other, ON plus and ON minus?
Yes, there's multiplicity. They're not multiplicity free, and they intersect.
But there must be some way to salvage it.
I
mean, how can this beautiful theorem be true just by numbers?
Yeah, no, I know. And I agree. And so this is why I'm looking for so I think you cannot get away from the combinatorial objects that underlie these characters. So unfortunately, so this, one of the things that I've seen in studying this stuff is that the answer is not group theoretic. The answer is not purely geometric. The answer is not purely combinatorial, but some combination of these things. And some people, I was reading about the classification of finite simple groups, and some people believe that there are these other objects that these sporadic groups are coming from, that finite simple groups of Lie type are just examples of. And this is some deep philosophical question about, but I think that once you start getting into finite simple groups of Lie type, and type A, sometimes there's a simple answer and sometimes there's not. And once you get away from type A, all of these other factors start entering in: the geometry, the combinatorics, the group theory. And I agree. I agree with you. There should be some nice answer. And I think for this particular equality, I think what it'll come down to is in Sn, so my strategy has been for Sn, there are 20 proofs of these facts. And each of these proofs has a chance of generalizing or might have some shadow in the group of Lie type. And so the model for Sn, which does translate to the number of involutions being the sum of the degrees, one can write down induced representations from centralizers of involutions, and it gives a model. And the way this translates to GLN somehow is this Klyachko model, where instead of symmetric matrices, one looks at these classes of skew symmetric things, and sometimes you have unipotent factors, and there's more geometry that enters in.
But that doesn't allow you to prove this theorem directly.
Exactly, and not directly.
It
and so what I think what's entering in here is that in the symmetric group, there's something called the Robinson-Shinstead correspondence there that corresponds a pair of tableau to a permutation. And one can correspond when those tableau are the same, you get involutions. And when you count the number of tableau, you get the hook length formula. And you get perfectly this Robinson-Shinstead correspondence says, if you group together these tableau and you have these hook lengths that you count, which counts the number of tableau, you get the number of involutions. And so what I think it's happening in the general linear group case is that as we see, there are these tableau which are underlying the characters. One can look at the symmetric group and one can look at the unipotent characters. And I think there will be some Robinson-Shinstead correspondence on the general linear case that counts on one side, happens to count the number of symmetric groups. Maybe you have these kind of tableau that are enumerated by symmetric matrices, and when they're invariant on some involution, you happen to have symmetric matrices. And I think something like this will happen. And I haven't done it. I'm not smart enough to figure that out, but I've brought it up to someone who specializes in these combinatorial things, and it's a question. I agree. It's an answer I would seek to find, and so this is my answer so far that I haven't. Well, it's not an answer. It's
just to change the topic, you said that the Schur indicator is invariant under this Alves-Curtis duality.
Yes.
There is a very cheap proof one can give. I don't know what was your proof.
Yeah.
Which is that, it is one if and only if the representation is defined over R.
Yes.
So if the representation is defined over R, all the modules are defined over R, and therefore that object is also defined over R.
Yes. So one just goes through the construction of Alves-Curtis duality, and you look at, that's exactly the proof. This is exactly the proof.
Okay, so it's kind of
it's intuitive. It works out very nicely. It works out very nicely.
I imagine that there is no simple character formula which relates the duality, no?
No. I mean, what does one have to do? You have to look at these parabolic subgroups, and then you look at the modules.
I think the character formula may be too complicated.
No, the character formula that's right. One does not use the character formula at all. Okay. One just does exactly what you say, follows the construction and says, these are defined by R, these are defined by R. In the end, the only tricky part, as you know, in the end, it's a generalized character. So you have plus and minus, there's this alternating sum that defines it. And
but if a representation is irreducible, then
that's right.
The Grothendieck group will unfold itself, and it will be defined over R.
Exactly right.
I think that looks okay.
That's exactly right. This is exactly how the proof goes. Yes. Yeah. Good. But the nice thing is that one can take your result on the regular characters, and when you dualize, you get semi-simple characters, which then tells you some nice information about the Jordan decomposition, right? Yeah.
Good.
And I will send a PDF.
You use this word generic character. I mean, there is something called generic degree.
Oh yes, there is something called generic degree, but this is.
I think you were using the word.
I know in p-adic groups, generic representation.
No, not in p-adic groups. No, I think there is something called generic degree and fake degree.
Yes, but these are a different. This is a different usage of generic. This is a different context.
No, but I think you said something about generic character, generic character table.
Oh yes, generic character table. Yeah, these are not generic. These are so the fake degree. I mean, this is some geometric concept, but generic character table. What I mean by that is that there is a character table for G2Q that is completely in terms of Q. So it's all computed. So you have all of the conjugacy classes of G2Q, and one can say exactly what all of the characters take values on all of those, and they're all just in terms of Q. So I meant generic in the colloquial sense, in that it's completely generic for Q. Yeah, it's one of these words that's used too much in math, I think.
Carter's book has the concept of a generic degree and fake degree. I have never followed that.
Yeah, this is a different concept. Yeah, this is some geometric concept that, and I think it comes up in the
again, it's due to Lustig, maybe.
Lustig, and I also think this comes up in this Curtis, and I mentioned this work last time. But this correspondence of Hecke algebras, it comes up with the Hecke algebras of the Weil group and representations of those. And who was that? Curtis and? Forgetting a name. I'm forgetting a name. But yeah, there's this correspondence of representations of Hecke algebras. And I think that these fake and generic degrees come from degrees that come from corresponding representations of Hecke algebras. Yeah. But I don't know it very well either.
Okay.
Alan Roche, who I believe you know, he has some idea of understanding the indicators going through the Hecke algebras, which I don't understand, but he has some idea of doing this. And hopefully once I can travel and do some work, I've been visiting Alan Roche in Oklahoma, and we've been doing some work. So this idea that's stemming from this, maybe some information on indicators can come from it.